Let's consider an example of how to write a Python program to display a vector field similar to the one down here. I am Ronald Johns. Our goal in this is to plot the vector field f of x, y, z equals the vector 3 plus x, 3 plus y, 3 plus z for x between -2 and 2, y between -2 and 2, and z between -2 and 2 inclusive. What we'll do is show a program that will do this for us, a Python program. We will briefly describe what duties each part of the program accomplishes. I'm not going to go into many nitty-gritty details in this case because there are many online web pages describing how to program in Python and how to use the various libraries that Python can offer, and in this particular case libraries that produce graphics and some mathematics. So in this program we will use functions that are in the libraries matplotlib, numpy or numpy, and also matplotlib.pyplot. These three will be used to call some functions so that we don't have to do very complicated graphing programs ourselves. The purpose is not to teach a course in computer graphics, but how to use functions that can produce the graphics for us. So let's see how we can draw such a vector field. We'll draw arrows with a three-dimensional perspective. So we'll import numpy as np, import matplotlib.pyplot as plt, and from mpl_toolkits.mplot3d we'll import axes 3d. Actually, in this program we do not need this last import. So here's what will happen. First of all, we're going to define a lattice of points in 3 dimensions where we want to draw little arrows representing our vector field. And we'll do it for x, y, and z, all going between -4 and 4. And for each of x, y, and z, we will plot 6 equally spaced points. And so x, y, z equals np.meshgrid, and then np.linspace -446, np.linspace -446, np.linspace -446. This will give us x values. They'll give us 6 x values going from -4 to 4. Similarly for the y values from this, z values from this. But what happens here is this actually is going to represent points in 3-dimensional space. And what's going to happen is we're picking 6 equally spaced values for x between -4 and 4 inclusive, same for y and z. And that gives us a total of 6 to the 3rd power, which is 216 points inside a cube, where the cube in the x direction goes from -4 to 4, in the y direction from -4 to 4, in the z direction -4 to 4. So it'll look like a cubic lattice, basically. Down here, u equals 3 plus x, v equals 3 plus y, w equals 3 plus z. This defines our function, our vector function f of x, y, z, our vector field. And when we draw the vector representing f of x, y, z, it's going to be represented by an arrow or quiver, which Python calls it, that starts at x, y, z and ends at the point x plus u, y plus v, z plus w, u, v, and w being given by these equations. So the direction of the arrow is given by u, v, and w. The starting point of the arrow in each case is given by values of x, y, and z, and the ending point of the arrow is going to be at 3 plus x, 3 plus y, 3 plus z. Okay, So then we declare a figure object using plt. plt was matplotlib.pyplot, and so from matplotlib.pyplot we're getting the figure function, and that creates an object called, in our case, fig. It's a figure, we're calling it fig. We could have called it fig1 or myfig or anything else here, as long as we're consistent later with it. We're also going to define an axis by this command. ax equals fig.add underline subplot 111 specifies the position as basically being the only one that we're going to have, just one there. You can read up on this later if you want to. And the projection we're going to have is 3D. So then, after we do all this, we're going to plot the vector field by using a vector function, which is actually a method for the object ax. And we'll explain what this function does later. But in any case, this fig command declares a figure object. It can contain plots or subplots, and as I mentioned, it uses the pyplot module. This line down here, ax equals that stuff, declares an axis. We picked its name to be ax. Could have used any name we want. It uses the fig object, which was defined by using the pyplot module. And in this command, we can use parameters that will specify properties of the x, y, and z axes. In this case, we didn't do it here. We could do it elsewhere too, we'll see. And as I mentioned, we'll look at this command, plus some others underneath. This is not the whole program, we're not finished with it yet, but we'll look at the rest of the program very shortly. Let's consider for a minute this statement. X, Y, and Z equal np.meshgrid of np.linspace minus 446, np.linspace minus 446, np.linspace minus 446. So as we mentioned before, we are preparing X, Y, and Z to take on values between minus 4 and 4, and there will be 6 points equally spread out for each of those. Well, you might think that X is just going to be minus 4 and then minus 3 point something and so on, but it's not quite that simple. It actually creates large arrays of numbers for each of these three variables, X, Y, and Z. And what happens is by using these three fairly large arrays together, we can look at every combination of values of X, Y, and Z between minus 4 and 4, such that the value of X, Y, and Z is determined by this np.linspace in each case. So what happens is you can think of it as maybe giving Z in terms of X and Y. For every X and Y possible values, you get a Z possible value. But the way that we wrote it here, it's not like Z was necessarily a function of X and Y. Z is just given values by this linspace argument here. X is determined by this, the values of Y is determined by this, the values of Z is determined by this. It might help you if you examine the values of X, Y, and Z after executing this piece of code. That can be done pretty easily by using the debugger. You could set a breakpoint after this statement is executed and then examine the values of the variables X, Y, and Z to see what's going on. One more thing to mention is that this sort of idea, this sort of statement, the idea behind the statement, is also used for preparing 3D graphing in MATLAB and Octave. Octave is very similar to MATLAB. It was designed that way. MATLAB is proprietary software. Octave is open source software. And numpy, from which this function meshgrid came from, numpy in Python was developed to be very similar to MATLAB. So let's look at the rest of the program. Here we're going to plot the vector field by this command, ax.quiver, parentheses, xyz, uvw, color equals blue, length equals 0.5, normalize equals true. Now what's going to happen in this case is the following. For each set of values of xyz and corresponding values uvw, Python draws an arrow, a quiver, having xyz as the location of the foot or beginning of the arrow, and the length and direction of the arrow are given by u, v, and w. Here we are setting the x, y, and z limits for the axes, all three of them, x, y, and z. See, we have set x lim, set y lim, set z lim. All of them in this case are going -4 to 4. Over here we're just adding labels to those axes. Set x label to x, set y label to y, set z label to z. These set, x label, and so forth are methods associated with the object ax, which are the axes. And then at the end of the whole program, we will plot the figure and the axes by using plt.show. So this will display the figure together with all of its plots, and in this case there was only one plot with one set of axes. As an example of what's going on with this ax.quiver, let's ask the following question. What would the quiver be if we wanted the vector field f at the point 1, 3, 2 to be the vector 2, 4, 6? In other words, we're going to have a vector out in space somewhere. It starts at the point 1, 3, 2, and this vector is 2, 4, 6. So what would be the coordinates of the end of this arrow up here? Well, we would get it by 1 plus 2 is 3, 3 plus 4 is 7, and 2 plus 6 is 8. And so to get this arrow drawn in a figure, we would use quiver 1, 3, 2, 2, 4, 6. The coordinates of the beginning of the vector, the arrow, and then 2, 4, 6 is the vector itself. When we execute this program, it creates this figure, which in this case is figure 1. It's a three-dimensional representation of the vector field. These are little arrows everywhere. If we want to, we can rotate this around. I'm just holding down the left mouse key and rotating this figure, so we can get a pretty good idea of what this looks like from various positions. Thank you for watching this video. I hope that it helped you understand the basics of 3D graphing of vector fields. A lot of the details are not mentioned in this video and can be found in Python documentation. Most of the documentation that you need can be found online easily by just searching for it. There are lots of web pages on how to write basic Python programs, and there are also more advanced web pages that describe and document the libraries that can be used in Python, including the graphics libraries that we used in this video. Thank you very much. Goodbye.